In this video, we are going to look at implicit differentiation. So in order to look at implicit differentiation, we first need to make sure that we have an understanding of what is meant by an implicit function. So let's first define implicit and explicit functions. All right, so when we look at implicit functions, or explicit functions, I suppose, a function that is written of the form y equals f of x, this is an explicitly defined function, right? So these are the functions that we're used to seeing. So you might have a polynomial y is equal to 3x squared plus 2x minus 1. You can find the value of y because it's written explicitly in terms of x. If I told you an x value, you could plug that in and roll through and find that y value very quickly, very easily. It is actually just the algebra of the stuff on the right-hand side. If you have y equals 4 sine x plus x squared tangent x all over 4x secant x, again, that's explicitly defined because we have y is equal to stuff only involving x. Right? It's okay to have constants like we had in the stuff above. The only variables showing up on the other side are those in terms of x. But we can also have functions that are implicit. Right? So a function that is not solved for y, so it's not solved for y, this is an implicitly defined function. So here, if we have something like x squared plus y squared equals 4, there's this relationship between x and y. We haven't explicitly written it down. We haven't written explicitly directly what y is in terms of x. But indirectly, we have said, oh, this y has this relationship to x. So implicitly, y is a function of x. Here, we have a lot of y's floating around, a lot of x's floating around. Ultimately, this boils down, y is some function of x implicitly, even if I haven't written it down, even if it's very, very difficult to write that down. We implicitly can understand that to be a function. And so when we go through and we want to take derivatives, we don't actually always have to solve for y. We can go through this process of implicit differentiation. Right? So with implicit differentiation, we can take the derivative of y with respect to x. So we can find dy dx of an implicitly defined function. So how do we do that? Well, we'll take the derivative of each term of the equation using our derivative rules. However, whenever we take a derivative that involves y is a function of x. So when we take the derivative there, we are going to have to use the chain rule. And then on the back end, after we've gone through this derivative, we're going to solve for dy dx. And so let's look at an example and see what's going on here. And so here we have x squared plus y squared is equal to 4. We want to find dy dx. So we want to find that derivative. So we're just going to go through piece by piece and take our derivative. What is the derivative of x squared? The derivative of x squared is 2x, which is great. Then we'll move to the next piece. What is the derivative of y squared? Well, y is a function, so it's 2y. We'll bring that power down, subtract 1 from the power. But the inside function is y, right? So our outside function is the squared stuff. The inside function is y. And so this is where we need to use the chain rule. So we need to multiply this by the derivative of the inside. The inside is y, and so when we take the derivative of y with respect to x, it is the derivative of y with respect to x. Right? So that's what we will write. That doesn't just magically go away. That is there. We're going to try to solve for that ultimately. And on the right-hand side, we need to take derivatives of both sides. We can't just leave that 4. We need to take the derivative of 4. Derivative of 4 is 0, because the derivative of a constant is 0. And now we want to solve this for dy dx. So subtract 2x from both sides. Then divide by 2y. get negative x over y. So our derivative dy dx is negative x over y. It might seem strange to have that y floating around in the derivative, but that's okay when we go through implicit differentiation. If I knew what y was explicitly in terms of x, if I had figured out how y can be written as a function of x, then I could replace this y with this function of x. But if I don't know that, I can leave it here. Implicitly, I know y has some relationship to x. Great. Let's look at one other example in this video, and then we will look at further examples in our next video. Let's look at this one other example. We're going to find dy dx for the following implicitly defined function. So we have x squared, y squared. So we need to take the derivative of this piece. When we take the derivative of that piece, what derivative rule or rules are we going to have to use? Well, let's read that out loud. So this is x squared times y squared. So we have a product of two functions. So when we take our derivative, we need to use our product rule. Right? So for our product rule, it's the derivative of the first times the second. The derivative of the first is 2x times the second plus the first times the derivative of the second. So we have 2y. Here we took a derivative of a portion involving y itself. So we need to use our chain rule, dy dx, plus the derivative of 37, which is 0, is equal to the derivative of 4x is just 4. Excellent. And so now we need to solve this for dy dx. So let's subtract 2xy squared from both sides. And then we will divide both sides by 2x squared y. So dy dx is equal to, we can call that 2 minus xy squared over x squared y. So there I factored out a 2 from the top. I guess I'll show you this in one quick step. So on the top we can factor out that 2. And so then those 2's cancel there, and we're left with our answer. That's how we find a derivative implicitly. We will look at some further examples in our next video. We will see you there.